All right, let's get right into it. When we talk about the future of AI, everyone's mind immediately goes to compute power. But here's the thing. While GPUs are getting faster and faster, the tech that connects them is about to hit a brick wall. So today, we're going to do an engineering first dive into POET technologies and what could be a truly radical solution to automate light for the AI revolution.
So here's the game plan. We'll kick things off with the big problem, AI speed limit. Then we're going to look at why the current way of doing optics is kind of handmade. From there, we'll break down POET's semiconductor solution and the incredible future it could unlock. And finally, we'll tackle the biggest question of all. Can they actually build it?
Okay, so let's set the stage. As these AI models get unimaginably huge, the amount of data that has to fly between all the chips is creating a massive, massive traffic jam. The electronic signals we've been using for decades, well, they're basically running out of highway. They're hitting a fundamental physical limit.
Yeah, everybody is laser-focused on the GPUs, the brains of the whole operation. But the real bottleneck, the thing that's going to slow everything down, is becoming the nervous system, those interconnects. Think about it. If you can't feed the beast fast enough, all that incredible processing power just sits there, wasted.
And believe me, the industry is not sitting still. The very next jump in speed is a big one. It doubles everything, going from 800 gigabits per second all the way up to 1.6 times terabits per second. A leap like that puts an unbelievable amount of strain on the old-school copper wires we've been relying on.
And that really brings us to the fundamental engineering challenge, right? How in the world do you connect all this stuff reliably at those kinds of speeds? How do you keep the signal clean and stable when you're shoving that much data that fast through a physical connection?
For any of you hardware engineers out there, you are nodding your head right now because you know this nightmare. Once you get to 100 G per lane, signal integrity on a circuit board just becomes this huge headache. Your signal degrades, power consumption skyrockets, and with it comes a ton of heat. You get jitter, attenuation. Basically, the signal gets all noisy and just falls apart before it even gets where it's going. We need something better. We need to use light.
So using light, photonics, that's the obvious next step. But there's a pretty big catch. The way we've been building optical components for years is, and this is going to sound crazy, shockingly manual. It's not designed for the kind of scale AI needs.
This quote just absolutely nails it. We are literally talking about tiny lasers, tiny lenses, and detectors being assembled with painstaking precision, often by hand or with these incredibly specialized slow machines. It's like building a Swiss watch. It's beautiful, but it's slow, and it's way too expensive when you need millions of them for your data center.
And the core of this high-tech watchmaking is a process called active alignment. You have to literally power up the laser and then physically nudge it around, tiny movements, nanometer by nanometer, while you're staring at a monitor, trying to find that perfect spot with the strongest signal. Now just try to imagine scaling that process to millions of units. You can't.
And this, right here, is where POET's technology comes in and just completely flips the script. Their entire idea is to take this manual, artisanal craft and turn it into a repeatable, automated process, just like we do with semiconductors.
Just look at the comparison. It's truly night and day. You've got the old way, super expensive, super slow, and just not scalable for what's coming. And then you have POET's approach, way cheaper, way faster, and it's all automated using standard equipment right at the wafer level.
So how do they do it? The secret sauce is their patented optical interposer. So picture a silicon wafer, but instead of just circuits, it has these incredibly precise little trenches and guides etched right into it. Then you can use standard off-the-shelf automated machines to just place the lasers and detectors into position. They literally self-align mechanically, snapping into place with submicron accuracy. No power needed, no manual nudging.
But wait, there's another really cool advantage here. The special material they use for these tiny light guides or waveguides has extremely low signal loss. We're talking less than 0.1 decibels per centimeter. So what does that actually mean? It means you can use less powerful lasers to get the job done, which directly attacks those huge power consumption and heat problems we were talking about earlier. It's a huge win.
So what's the big end game here? Where's this all heading? Well, all this miniaturization and automation opens the door to the industry's holy grail, co-packaged optics, or CPO. This is what everyone wants for next-gen AI hardware. It's where you put the optics right on the same package as the processor itself, basically eliminating the distance that electrical signal has to travel.
And because this whole process is done at the wafer scale, the final optical engine is just tiny. I mean, look at this. We're talking about a 4x size reduction compared to a traditional pluggable module you'd use today. And that compact size is absolutely critical for CPO, where real estate next to the processor is everything. And it's not just smaller, it's way, way simpler. A typical optical module might have 30, 40, maybe even 50 different little parts that all have to be put together. With the optical interposer, that whole mess gets boiled down to about 6 components. That is a massive simplification in manufacturing and a huge boost for reliability. Fewer parts means fewer things can go wrong.
Now, for the layout engineers out there, this is where you really start smiling. By integrating everything onto one chip, you get rid of all those messy little wire bonds, which are a huge source of signal problems. That means you're minimizing all that electrical noise, things like parasitic inductance and signal reflection. All of a sudden, your high-speed design and your thermal management just got a whole lot easier to handle.
And what's really powerful is that this isn't some closed proprietary system. It's an open platform. That means you can mix and match the absolute best components for the job. It's like building a fantasy team. You can use super powerful lasers made from one material and pair them with ultra-fast modulators made from a completely different material. This hybrid approach is what gives it a clear, engineered path to 3.2T and even faster speeds down the road.
But of course, you can have the most brilliant technology in the world, but it's totally useless if you can't actually build it at scale. And that brings us to the final, and probably the most critical hurdle of all, making that jump from the lab to high-volume manufacturing.
So POET is really at this make-or-break moment. They've validated the engineering, they've launched their production facility over in Malaysia. The next huge milestone on the calendar is shipping those 1.6T samples out to customers, which is slated for the second quarter of 2026. And the goal from there is to ramp up to a 1 million unit annual capacity by the end of that same year.
Now, look, it's worth noting there has been some noise around the company, particularly from short sellers focusing on finances and things like that. But from a purely engineering standpoint, which is what we're focused on today, the only thing that truly matters is performance. At the end of the day, the data that comes back from those customer samples in 2026, well, that's going to be the ultimate proof.
So to wrap this all up, let's just boil it down to the core value. Number 1, POET transforms optics from a high-tech handicraft into a modern semiconductor process. 2, it solves one of the biggest problems for silicon photonics, how to integrate a light source cheaply and efficiently. And 3, it creates one of the most direct and viable engineering paths to that co-packaged optics future that the AI industry so desperately needs.
The technology itself looks solid. The engineering path seems clear. The only question that remains is a really, really big one. Can the factory ramp up fast enough to meet the absolutely insatiable demand of the AI industry? That is the story we are all going to be watching.